amplifier and number of amplifier. This is just a constant value, okay? And if the AC noise from the booster amplifier can be ignored, only if the span loss L is much greater than the booster amplifier gain, that's just a difference. This one disappeared, the contribution of a booster amplifier. So you can take this equation. And if a single span with the only booster amplifier, that means that this, in this case, only booster amplifier, this N disappear, and you can get this equation. And only a single span with a preamplifier. In this case, this preamplifier's case simplified in such an equation. Only a L. L means gain of the preamplifier. Okay. And the repeater spacing required to achieve typical transmission distances. So repeater, as you can see, if you increase the repeater spacing, for example, 50 kilometers to 100 kilometers, the amplifier has a larger gain. So the larger gain means a larger noise. So you have to take into account the other design important design parameters as a repeater spacing in the system. So the system length increase, the possible repeater spacing decreases to maintain the OSN object. For example, a link up to 2,000 kilometers, for example, maybe a terrestrial line. The repeater spacing can be, for example, 80 to 100 kilometers. But for transoceanic submarine links, maybe 6,000 or 8,000 kilometers, the maximum repeater spacing is around 50 kilometers. Yeah, so this is a trans-Pacific system, means trans-Pacific distance is about 10,000 kilometers. So we have to reduce the repeater spacing. But in the case of trans-Atlantic system, we can extend the repeater spacing a bit to 60 kilometers or so. Or do you know the distance of a transatlantic distance from USA to Europe, or Europe city, maybe France or something? Do you know? About 6,000 or so, 6,000 to 7,000, depends on the route of the submarine cable route, maybe. And the trans-Pacific means the 10,000, exactly saying 9,000 kilometers from Japan to USA. Okay, we have a microphone.
Thank you. Why in terrestrial links you have big distance between repeaters than transoceanic? I mean, why you have, when you want to put repeaters between two, you need to put repeaters. For terrestrial links, you have big distance than transoceanic submarine links. Why?
Do you mean that why this?
Okay, let's take an example. For terrestrial link, you say that repeaters should be spaced between 80 and 100 kilometers. This is the maximum. After 80 kilometers, you put a repeater. But for submarine links, you put it up. The maximum distance is 50 kilometers. Why is it shorter than terrestrial?
Okay, I see. So the reason why for longer distance systems we have to use shorter repeater spacing. Okay. As you can see, this figure, this OSN are degraded by the loss of the repeater spacing. That means the fiber loss. So if you reduce this fiber loss in each repeater span, the OSN can be improved for the same output signal power. So for longer system, you have to you will incur the more noise. More noise. That means the OSN will degrade. I mean that if in longer systems, this number of amplifiers increase. It's a clear number of amplifiers increase. So if you accept such an increase of number of amplifier, you have to reduce this loss to compensate for the increase of number of amplifier. So you have to reduce the loss of each section or each gain of amplifier. Okay, now talk about the signal power is the same for terrestrial system and submarine longer system, same power. And we need the same OSN value for longer transoceanic systems and terrestrial system. Same OSN have to be achieved. So then the longer system will have so many number of amplifiers. So this could degrade the OSNR, but if we reduce this L is the loss of fiber, each fiber section, you can compensate for the increase of this degradation by reducing this value. So I mean the longer system, you will need to reduce the repeater spacing. Okay. Anyway, you can ask me later if you don't understand well. It's a bit complicated, this situation. And this is just another example of unequal amplifier losses of the spans. If the amplifier span loss is not equal, then we have to use this equation. That means OSNR has to be calculated for each span. Okay, so you use such an equation, but it's just a deformation of the previous equation. So just complicated. And again, I told the penalty due to chromatic dispersion. So optical amplifier solves the attenuation problem. That can optical amplifier increase the signal power level attenuated by the fiber. But this amplifier doesn't restore the amplified signal to the original signal. This means that the amplifier just amplifies the signal and doesn't shape up the distorted signal, just amplify, not reshaping the pulse. So dispersion induced degradation of the signal accumulates over multiple amplifiers. That's the simplicity. Dispersion will accumulate. So, and strongly limits the maximum transmission distance of optical amplifier. Or use of narrow line width lasers and operating close to the zero dispersion of the fiber will avoid this problem. But this is not practical always to operate near the zero dispersion wavelengths because of the fiber nonlinear effects. I will describe later fiber nonlinear effects. Oh, okay. Yeah, please.
Can you come back? Okay, I don't understand something. In your first line, you tell optical amplifier solve the attenuation problem, and you tell optical amplifier does not restore the amplifier here to the original state. I don't understand.
Okay. This description is just when you use not optical amplifier but regenerators, electrical regenerators. The regenerator has a so-called 3R regenerator: retiming, reshaping, regeneration. Okay? That's a 3R regenerator. So reshaping means that if the signal path degraded, but the signal can be restored to the original shape like a clean digital pulse. This is reshaping if you use the regenerators in the system. But optical amplifier just amplifies the amount of the signal. So if you have a degraded signal put in the amplifier just increase the amplitude of the signal, but just this signal is in proportion to the original input signal. That means the amplifier don't care about the signal is degraded or not, just amplify. So you will see the same waveform as the output of the amplifier as the input waveform. So waveform distortion can't be restored by the amplifier, just accumulates. Okay, amplifier is just the same as the fiber, just amplify, nothing to do.
Okay.
And next, this is simply dispersion accommodation or compensation. So dispersion accommodation cancels the pulse broadening caused by the chromatic dispersion. This is just, for example, if you use G.652 fiber, the large dispersion value, and the dispersion effect will be accumulated at the transmission distance. But you can compensate for this accumulation of dispersion by using such a dispersion compensator. This is very simple. Dispersion of the transmission fiber and the length should be equal to the dispersion compensator's dispersion value and dispersion length. Dispersion compensation method, there is also active and passive method. Active method is just something device to compensate for the chromatic dispersion. And the passive method means the dispersion compensating elements along the fiber link. Normally, this is a dispersion compensation fiber. Just a fiber has an opposite direction of dispersion as the transmission fiber, like this. So usually we use this dispersion compensation fiber to compensate for the fiber of chromatic dispersion of optical transmission fiber. Okay. So this is the configuration of such a passive dispersion compensation for line amplifier. So this is the most widely used technique and actually defined in the G.691. It's dispersion accommodation technique. And this is the configuration. For example, we contain the two EDFA, but we assume that this is the one amplifier. And the first amplifier amplifies the signal, but there could be some loss by this dispersion compensation fiber. And again, we will amplify the signal. So input and output, anyway, the signal could be amplified by using this optical line amplifier. So passive dispersion compensation means this dispersion compensation fiber or fiber grating or some technologies. Yeah. And this DCF can also be used in a booster amplifier at the transmitter side or preamplifier at the receiver side. Of course, the most popular use is just such mid-stage of optical amplifier is popular use of this technique. So this is a so-called dispersion map. Dispersion map means a picture of the behavior of the chromatic dispersion along a link. This is a transmission distance, and this is the accumulation of chromatic dispersion. So as you can see, passive dispersion compensator can exactly compensate for the chromatic dispersion for one wavelength, but not exactly at the other wavelengths. This figure shows that for each wavelength channel, 1542 to 1557 nanometer or so. This is so. This zigzag means that this is a dispersion by the transmission fiber, but you can place a compensator. You can place a compensator to reduce the dispersion value to zero accumulation. And again, transmission fiber, and again, compensation. You can see such a shape of dispersion value along the transmission distance. And you can transmit a signal. And in total, zero dispersion. So that means no waveform degradation along the distance by using such a dispersion compensator. But the problem is the difference in residual dispersion between channels can be minimized by applying dispersion compensation, dispersion slope compensator together. This means you can compensate the dispersion, chromatic dispersion by dispersion compensator. But I said just a chromatic dispersion. But in this case, chromatic dispersion means the so-called second order group velocity dispersion. Do you know? Chromatic dispersion has so many kinds of dispersion. So first order, second order, third order, or more higher order dispersion. And we are focused on mainly a second order dispersion, group velocity dispersion. That causes a waveform distortion of a transmitted signal. But actually, a slightly small amount of higher order dispersion. That means so-called second order group velocity dispersion. We mainly focus on the first order, normally GVD, group velocity dispersion, but there could be a third order dispersion. So that means you can't compensate all the signal channels where to compensate for this dispersion value. Only for the specific, maybe this case, center wavelength channel can be compensated perfectly. But those signal channels differ from the center wavelengths. We can't compensate the dispersion value perfectly. So we can compensate, but slightly different the compensation value, so the accumulation will generate such. So the blue line will suffer from such a dispersion accumulation, and this longer wavelength signal will suffer from such a non-negligible accumulation of dispersion. This means that because of the higher order dispersion. So we need higher order dispersion is, in other words, dispersion slope compensation. Yeah? In addition to this dispersion compensation and dispersion slope compensation. And another problem is that chromatic dispersion in the fiber may vary with time or temperature, and the high-speed system may need, if very long systems, passive chromatic dispersion compensator and dynamic adaptive compensation. This could be the same situation as the PMD and 40G systems or so. So, any questions about dispersion? No? Okay.
Okay. I want to know in this picture, why is a place you can see the cosmic dispersion in fiber? Maybe you tell vary with time, temperature, and high speed. Can you explain this in the picture? The 2 points. Yeah. You don't understand me? Why in the 2 points, the cosmic dispersion in the fiber may vary with time, temperature, and high speed system. Can you explain this in the picture?
Of course. And if the time varying or temperature change, the dispersion value of transmission fiber will change. That means this dip or value will change to lower or higher. But if dispersion compensation doesn't change, this waveform, like a line, will be shifted to such a slope or such a slope. So it depends on the temperature or time, so slightly. And this is problematic for high-speed signal transmission because once we set the dispersion compensation value to be the best value for the system, but later we will incur some degradation by the temperature change because the setting will be changed. Okay? Crosstalk between something to something. The crosstalk in the optical system is the transfer of power from one channel to another. So crosstalk occur in even linear system, linear channels. So imperfect nature of WDM components or filters or demultiplexer or photonic cross connects. And the cross connect can occur due to nonlinear optical crosstalk also can occur due to the fiber nonlinear effects in optical fibers. So I will describe the fiber nonlinear effects later. So two kinds of optical crosstalk, you have to consider two kinds of optical crosstalk. One is interchannel crosstalk, and the other is interferometric crosstalk. The difference of interchannel crosstalk and interferometric crosstalk is that if you have electrical signal, optical signal, this is described the electrical field as E signal and the crosstalk signal, two signal. Then you will detect those signals as a receiver as optical power. That is the definite value of this electrical field is power or intensity. And if you calculate this equation, you can see three terms here, signal itself. And this is a so-called interaction between the signal and the crosstalk, this cross term. And the crosstalk intensity itself. And we say this value, crosstalk power itself against the signal power. This is just an interchannel crosstalk. And another one is this cross term between the signal and the crosstalk signal electrical field against the signal power. This is interferometric crosstalk. The two kinds of crosstalk we will see in the receiver. And this could be less problematic because you can eliminate this if you increase the signal power itself. But this time, interferometric crosstalk is problematic because as you can see, if you increase the signal power to reduce the relative power of the crosstalk, but this case, you may increase also this crosstalk with this signal power increase. So this interferometric crosstalk is more problematic for the system than the interchannel crosstalk. Okay? Just a simple calculation. There are so many terminology in optical crosstalk, so I don't describe so details, but you can see in your handbook such kind of parameters like interchannel crosstalk, interferometric crosstalk, interchannel crosstalk penalty, interferometric crosstalk penalty, channel power difference, just a difference between the channel, and extinction ratio, or eye closure penalty, or insertion loss, or unidirectional isolation, adjacent channel isolation, non-adjacent channel. Anyways, there are so many parameters concerning the optical crosstalk. So let's see this example for interchannel crosstalk. So as I said, interchannel crosstalk is caused by the imperfect multiplexing of a multi-channel transmission signal in the individual channels. This is the demultiplexer. So you have such a WDM signal, and each port has divided signal channels. But in the case, let's see this channel. Okay, after the demultiplexer, this channel can be divided only one signal channel, but imperfection of this demultiplexer can cause very small crosstalk from the other channel. You can see such a spectrum at the output of the demultiplexer. So this can be a crosstalk. And we defined this is just a nominal demultiplexer loss. The signal is smaller than others by D. And the crosstalk is that the demultiplexer crosstalk value is this value, yes, between the signal you want and the signal you not want. This is the crosstalk value. And this value, you want signal, you want this signal, but this signal is smaller than others. The crosstalk value will be larger, or isolation is decreased because this signal is smaller than the others. But normally, if the level is the same, the crosstalk is given by this level. And you see that this is just a crosstalk power. In the previous figures, that's EXD square. This is small fraction of crosstalk. And this is a just signal, okay? And what is the interferometric crosstalk? When the disturbing signal channel and the wanted channel are the same nominal wavelengths, or when the two optical signals are sufficiently close together that their beat frequencies within the electric boundaries of the receiver. This is a case that as you can see, this is maybe 100G or so. This is could be a DWDM system, 100G. And you will detect at the receiver only this signal. And you don't care about these signals, just the power, just optical power. But if this distance is so close and you will receive both signals, signal you want and the signal you don't want at the simultaneous inside the receiver bandwidth, that's called interferometric crosstalk. Okay. So actual case is in an optical add-drop multiplexer where the wavelength is question is incompletely dropped before the new signal is added. This means that if as OADM max, you can drop any signal and add the new signal for the same wavelength. And the device is not perfect. There could be some fraction of the signal. The signal could be the same wavelength as the added signal. So added signal and crosstalk signal are the same, almost the same frequency. That could be the interferometric crosstalk penalty. Okay. And optical multiplexer, this maybe emit power at the receiver inside the model separation rate. So this is just for the a laser issue or cross connect. The lack of sufficient switch isolation causes light from more than one source fiber to reach the receiver. That means for the type of 3D MEMS or WSS devices, some signal can be enter the another port or channels if the isolation is not perfect. Like that, the more than optical path that light can take to reach the receiver. So anyway, the almost near the same position in wavelengths or the same wavelengths, the receiver can detect both as a signal. Okay. In such a case, I described that if you use such a MEMS mirror type switch, and you want to connect A1 to, for example, B1. Now connect A1 to B1, and you will change the combination of the optical port from A1 to B3 to change. But when you change the port, you have to change the mirror angle. So mirror angle, if you change you will pass through possibly this direction. Optical beam will pass through this direction, and possibly this mirror will reflect the signal instantaneously and couple to this port. So if this port are already used for the other signals, this could be the crosstalk. Okay. And this is just a penalty due to optical crosstalk. Simply calculation of optical power penalty is for the crosstalk value. As I said, intra-channel crosstalk means the interferometric crosstalk and the inter-channel crosstalk. So as you can see, the difference in penalty for both type of crosstalk. So as I said, interferometric or intra-channel type crosstalk is much problematic than this inter-channel crosstalk. For example, minus 40 dB crosstalk will cause 0.1 dB optical penalty, or minus 30 dB, 0.3 dB penalty. So you can remember the value that's about minus 30 or dB or so. It could be acceptable value level of the crosstalk in the optical system. This is figure is in your handbook a bit complicated, so I don't describe so detailed, but this is for inter-channel crosstalk. This is the inter-channel crosstalk value and optical penalty value. So for the there are many combination of system parameters like that. Okay. And this is also for interferometric crosstalk. The calculation results described in G.698.8.2. So as you can see that this value is so problematic for optical system. Another issue is, this is not described in the handbook, but actually important issue, so I added this contents. Actually, optical amplifier's bandwidth is not flat, so ideally. Thus, so the signal passing, as signal passes so many amplifiers, the combination of the amplifier gain spectrum can change shape of the WDM signal, so alignment in terms of the power. So even if we send the WDM signal at evenly spaced, evenly powered, but if you have such a non-flat optical passband, the signal power difference will cause some degradation because some signal channel power will be decreased compared with others. So gain profile of optical amplifiers are not enough flat, especially for a wide range of optical bandwidth range. So when you use so many wavelengths in your system and long distance, this means many cascades of optical amplifiers, number of optical amplifiers. So in such a case, we will take a technique of so-called gain equalizers that equalize the shape of this optical amplifier shape, gain band shape. The principle is not so difficult. So as you can see, for example, Fourier expansion is that synthesize any shape or function by multiple Fourier components. And this is the example. This is just actually optical band amplifier shape, S-band shape. So we need to compensate for this shape. So we synthesize as like many Fourier components, gain equalizer, and we can make just reverse shape of this amplifier gain shape, amplifier response. So we can flatten the spectrum by using this type of filter or equalizer to adopting this amplifier's gain bandwidth. So this is the actual example of the transmission experiment by using this cascade of optical filters of gain equalizers. This is, I I don't remember the transmission, but 3,000 kilometers or so. If you don't use with gain equalizer, such as signals are unequally arranged. So this means that even the WDM signals, you have to transmit all the WD channels correctly to the receiver. But as you can see, around this channel has so low power, low OSNR. So those signals cannot be used even the WDM system. So for such system, if you adopt a gain equalizer, gain equalizer, this shape of gain equalizer, you can flatten the spectrum of the WDM signal. But if we use the gain equalizer for number 2, but for gain equalizer, if you use more flat, clear WDM spectrum can be obtained by using this gain equalizer. So you can transmit all the WDM signal channels with a good quality as a receiver. This is the bad quality around here, okay? This is the gain equalization techniques in optical amplifier systems. Any questions? Okay. So shall we start to the fiber nonlinearities? So this means a nonlinear interaction between the optical signal and the transmission medium. That means the optical signal power is increased for longer span lengths at high bit rates. This means as we need to transmit large capacity or high speed signal, and as we increase the transmission distance, the optical SNL value will decrease as the increase the capacity or increase the distance. So we have to increase the signal power to improve the OSNL, because OSNL is just a ratio of signal power to the noise power. So we will, it may be better to increase the signal power for larger capacity and longer distance. But you will be limited by this fiber nonlinearities. So you can't increase the signal power anymore by such a fiber nonlinearities, because nonlinearities will be significant in as you increase the signal power, because fiber nonlinearity is just a nonlinear. Fiber nonlinearity could be remarkable at a higher power region. Okay, and I will describe each fiber nonlinear effects later. But anyway, nonlinear effects can be generally categorized. So the scattering effects, this means stimulate brilliance scattering or stimulate Raman scattering. This is often used for Raman amplification. But in this section, we say stimulate Raman scattering. And another one is the effects related to the Kerr nonlinearity. Kerr nonlinearity means the fiber's refractive index will change according to the optical power. So optical power changes, refractive index of fiber will change. This is the fiber nonlinear effect. This is the intensity dependent refractive index. So this categorizes self-phase modulation, cross-phase modulation, and four-wave mixing. So as I say, the influence of nonlinear effects, nonlinear phenomena increases with the optical input power. So the degradation at low fiber input optical power. That means we can't increase the optical power, so we have to accept such a lower OSN. So we need some compromise between the minimum input power level, so-called OSNR limit, the maximum output power. This could be limited by nonlinear effects for system performance. That's we will have a lower limit by OSNR limit, noise limit, and a higher level limits by this fiber nonlinear effects. So a variety of parameters in addition to the optical input power, dispersion, nonlinear coefficients, the effective area of the fiber, or the degree of uniformity or something like. And the signal, system parameter, number and spacing of channels in WDM systems. or unrepeated system length or source line width or like that. Now I describe the stimulate brilliance scattering. Do you hear stimulate brilliance scattering or SBS in a transmission system? This could be the problematic for when you input the higher power to transmitter for long distance system transmission. And this could be caused by the molecular vibration of the glass fiber is glass, so glass itself. So this is just a simple model of the vibration of glass molecule. So this stimulate vibration brilliance scattering means this material will oscillate, vibrate. Two materials can vibrate in the same direction. As you know, in this system in physics, this spring system means that there are two modes of vibration. One is these two particles move the same way, this mode. And another mode is opposite direction. There are two kinds of mode of oscillation in such a physical system. And the brilliance scattering corresponds to this moving the same direction, like that. So what happens if the molecule or material in an optical fiber moves such directions? There could be made black grating. Black grating means like dense sparse, the repetition of the diffractive index along the fiber. Do you know the grating? Grating means this repeated difference in diffractive index, such as shown in this figure. Okay. So once such a black grating are made in the fiber, the input light will be reflected by this direction. The direction could be determined by Bragg condition. Bragg condition means that's phase matching condition of the signal and the reflected light. So most case, or exactly saying, in the optical fiber, brilliance scattering light is coming back from the fiber, not forward direction. We will put in the light to the fiber, but brilliance scattering will scatter the signal light to the backward. So you can see the backward brilliance scattering light in this system. So this means a significant optical power transfer from a forward propagation signal to a backward propagation signal. This is just a Doppler shift caused by acoustic phonon. Doppler shift means that this is just a moving molecule, so the back scattered light will be a bit shifted from the original input signal. So this is a Doppler shift. Okay, and SBS stimulated brilliance scattering threshold is sensitive to the source line width and the power level, and the optical power should be above the SBS power threshold. And as I described, the scattered light will be downshifted by the brilliance shifting. So about 11 gigahertz at around 1,550 nanometers. And this SBS behavior will vary with fiber types 652 or 653 or something like that. And the 5 to 10 milliwatt for external modulated and narrow line with source, but 20 to 30 milliwatt for directly modulated lasers. This is because the directly modulated lasers has a wider chirping and spectral width, as you see in chapter 5. So broadened spectrum can be effective for reducing stimulate brilliance scattering. This is a okay. this figure shows the actual measured results of brilliance scattering. This is injected power for the fiber, and this direction, this is the output power through the fiber, forward direction. And this is scattered light to the backward direction. Okay? And a narrow band source is effectively called the stimulated brilliance scattering, because the brilliant bandwidth is very narrow. So only the signals within this narrow brilliant bandwidth can be backscattered. As a result of this SBS, if you input signal power and increase the injected power, output power will increase, of course, only the fiber loss increase. But if the optical output power is above this threshold value, you can't send optical power anymore, so saturate. Instead, the power you injected the optical fiber will be effectively backscattered by the SBS. So the SBS power will increase instead of the saturation of this transmitted power. So this, around this level, we call the SBS threshold, because the SBS backscattered power can be detectable from around here. So we say SBS scattering. Sorry. So important thing is that if you want to input the large power into the fiber, just simply saying you may increase the signal bandwidth of the transmitted power to reduce the SBS stimulated brilliance scattering. Okay, and fortunately, we will have a 10G system or 40G system, so we will have modulation of a signal, not as single spectral, but modulation causes the spectral broaden, 10G or 40G. So signal power will be scattered along the bandwidth of the transmitted signal bandwidth. So we can effectively reduce the stimulated brilliance scattering. So nowadays, this SBS is not so problematic in actual optical amplifier systems. Then I will describe the so-called stimulated Raman scattering. So as you see in the chapter 5, that's Raman amplification. Raman amplification is when we input a pump power to the fiber will have such a gain spectrum, so this can amplify the signals. So we say Raman amplifier. But here we say Raman amplifier, not Raman amplifier, but Raman stimulated Raman scattering, the same thing. And this effect could be understood as impairment, not benefit, just impairment. So the effect of Raman scattering is just if WDM system, you have this signal, but this signal will cause such a gain spectrum, Raman gain spectrum. Then this signal, the longer wavelengths could affected by this gain, so amplified a bit. And this signal will decrease. As a result of such an effect, even if you transmit a double signal in equal signal power levels, but after such a Raman scattering, a WDM signal will, in a short wavelength range, decrease. The longer wavelength range will increase. So there could be an imbalance between the WDM signals. And as you can see in the previous section, that you will need some gain equalization for compensation of such imbalance. So Raman scattering will also cause the imbalance between the WDM signal channels, and this is problematic. And SRS stimulated Raman scattering is a different mode of oscillation in a vibration oscillation of fiber material. As I see the SBS, in the case of SBS, the particles are moving the same direction. But in the case of SRS, the mode is different, so opposite directions, oscillation. That is the difference between the stimulated fringe scattering or stimulated Raman scattering. Okay, I said around here. And the capacity limitation, the total number of channels or channel spacing or average input power and the overall system length. And actually no practical techniques to eliminate the effects of stimulated Raman scattering. Just we can't have any countermeasure to this effect. Maybe just decrease the signal power. And this is just so-called stimulated Raman scattering threshold. This threshold is deployed on the D.6535 fiber. D.6535 fiber is slightly lower than that of a system using 652 fiber. This is because the 653 fiber has a smaller effective area, so the threshold levels are a bit slightly smaller than the 652. This is just equation. If you want to calculate the SBS threshold as a combined power of all of the channels, optical spectrum over switches over which the channels are distributed, or effective length means just a fiber length and calculated from the fiber length and considering the power distribution along the fiber. And this can be used for calculation of SRS. So again, this is a nonlinear effects due to Kerr nonlinearity. As I said, there are two kinds of nonlinear effects. One is a scattered effect, and the second one is Kerr nonlinearity. So Kerr nonlinearity means that diffractive index changes with the optical intensity in the fiber. The fiber's diffractive intensity change. So what happens if the diffractive intensity change with the optical intensity or power? So this phase shift, this called the phase shift of optical signal propagating in the fiber. The phase of the optical signal will be modulated by such a nonlinear effect. So this depends on the optical power in the fiber, length of fiber or propagation distance, and nonlinear coefficient of the fiber. This means that in equation, nonlinear refractive change described. This is a normal linear refractive index, and A effective is core area amount large or size, maybe D.652 fiber. This A effective is large, so nonlinear effect is smaller. N2 is nonlinear refractive index of fiber materials, and this is power. As you can see, that the nonlinear refractive change is dependent on the optical power. And this is a nonlinear phase shift caused by the refractive change. The nonlinear phase shift is caused by this power and the length of the fiber or transmission distance. So as I said, the Kerr nonlinearity effect of Kerr nonlinearity is very significant for high power and long distance systems. And this is a optical intensity in the optical fiber, as the same as the crosstalk. This electric field, if the electric field is the sum of the two electrical fields, then the power is described. This is just if E1 is a signal, and E2 is something disturbing, unwanted one. So E1, power E1, the signal intensity. So this causes self-phase modulation. This means that phase modulation caused by the signal power change itself. This so self-phase modulation. And this is interaction part between the two electrical fields. This is interaction of signal and noise, so-called four-wave mixing. Four-wave mixing, the meaning of four-wave mixing will be clarified later. Anyway, we say four-wave mixing. And this is unwanted channel intensity change. So I describe here noise intensity. This means the cross-phase modulation. In many cases, cross-phase modulation refers to the phase modulation caused by the other signal channels in WDM transmission systems. Signal channels you see, and the other signal channels change will cause the phase modulation to the signal you want. Okay, so this is a simple figure of self-phase modulation. So you can see this signal path. This is the intensity. And this intensity change causes a phase change of the signal. So phase change means that this frequency change like that, frequency of signal. So you mean you see that signal frequency will change depending on the time. As you can see this such as so modulated. The effect of self-phase modulation can be understood by the spectral broadening. Like this figure, this is actually measured spectrum of the signal. This before transmission, you can see a smaller area of the signal spectrum on narrow line with this. This is actually 10G signal, but very narrow. And after transmission, 3,000 kilometers or 6,000 kilometers, the spectrum spread, as you can see. This is caused by phase modulation of the signal. The phase modulation caused by the self-phase modulation, nonlinear effect. So this is problematic because such a broadened signal can suffer from the chromatic dispersion distortion because the signal boundaries became so wide. So chromatic dispersion effect can be easily affected by the chromatic dispersion. Okay. So system impact of SPM. So the effects of SPM are significant, but phase modulation leads to unwanted spectral broadening of the pulse, as I said, and suffer from high cumulative dispersion in very long systems. The spectral broadening may also create interference between adjacent channels in multiple channel systems with a very closely spaced channel. This means if the signal spectrum will broaden, the broadened spectrum will emerge to the neighbor channels, so that could cause crosstalk. Or if you have a narrowband optical filtering at the receiver side, the spread spectrum will be rejected. Some of the spectrum will be rejected by the narrowband filtering, so degradation will cause. And distortion penalty of SPM means that higher channel bitrate will be increased effect and reduced by G.53 fiber and their signal channel near the dispersion zero. And controlled by the implementation of dispersion compensation at appropriate intervals along the length of the G.652 fiber. This means the dispersion compensation fiber will be used as you see at the dispersion map. You can compensate the dispersion value by the compensator, and the effect of dispersion could be reduced. Or SPM can be mitigated by the use of zero dispersion wavelengths. That means less effective by the dispersion, chromatic dispersion. Or use any fiber with increased fiber effective area or lower nonlinear refractive index. Okay. And SPM effects may be reduced by decreasing the launch channel power. Of course, this is nonlinear effect. Yeah? System designer needs larger powers for system design needs, but larger powers for larger capacity and longer distance. So we have to have some compromise between the signal power. So another effect, I see cross-phase modulation. As I described in the previous slide, we will have 3 nonlinearity induced effects: SPM, cross-phase modulation, and 4-wave mixing. This is the second one, cross-phase modulation. But the situation is almost same as SPM, because the SPM is phase modulation induced by the diffractive index. But this is the cross-phase modulation, means phase modulation by the other signal channels, not signal itself. So this is changes the optical phase of the signal by the change in the intensity of adjacent channels in multi-channel system. So this also broadens the signal spectrum, as the same as the SPM. And the amount of spectral broadening is related to channel separation in the fiber chromatic dispersion. So if the channel spacing is wide, it's less effective. The signal experiences a greater temporal broadening as it propagates along the fiber due to chromatic dispersion. The signal experience so effect of chromatic dispersion, because temporal the spectrum could be broadened. And the system penalty from cross-phase modulation is increased by smaller channel spacing and larger channel counts. So the signal could be affected by the cross-phase modulation by so many signal channels. And the signal channel spacing is closely located, the impact will increase. But dispersion, in this case, dispersion induced differential group velocities will reduce the interaction between the signal pulses. This means the interaction time will be shortened in the fiber system with the chromatic dispersion. Because as you can see, the signal will propagate at slightly different speed due to chromatic dispersion. And the interaction between these channels will be decreased if the